Good day and welcome once again to our class. In today's class, we are looking at the convergence and the divergence of series. Convergence or divergence of series. And we'll be considering the various ways to determine if a series converges or diverges. In order to determine whether a series converges or diverges, there are tests that can be carried out. The first one is what we call the divergence test. Given the series summation a sub n as n moves from 1 to infinity, then summation a sub n diverges if the limit as n tends to infinity of a sub n is not equal to 0. If the limit is not equal to 0, then the series diverges. However, if the limit as n tends to infinity of a sub n equals 0, it implies that the test is inconclusive. As such, other tests need to be carried out to determine whether the series actually converges or diverges. The divergence is one of the simplest tests that can be used to determine whether a series diverges or not. The next test is the geometric series test. We are familiar with what we call the geometric series. It is a series that can be written in the form a times r raised to power n minus 1. Therefore, given this series summation a sub n as n moves from 1 to infinity, such that a sub n can be written as a into r raised to power n minus 1, where r is the common ratio. Then the series summation a sub n as n moves from 1 to infinity is said to converge if the absolute value of r is less than 1, and to diverge if the absolute value of r is greater than or equals to 1. Remember, we have said that what? Our r is the common ratio. However, the sum of the series s, which is the same thing as the summation of a sub n as n moves from 1 to infinity, is equal to what? The first term over 1 minus r. The first term over 1 minus r. We move ahead to the P series test. Again, given the series summation a sub n as n moves from 1 to infinity, such that a sub n can be written as 1 over n raised to power p. Then the series converges if p is greater than 1 and diverges if p is less than or equal to 1. That is the P series test. The next thing we want to talk about is the integral test. Given the series such that a sub n can be written as f of x, then the series converges if the integral of f of x as x moves from 1 to infinity is equal to a finite number L and diverges if the integral of f of x is equal to plus or minus infinity. However, to make use of the integral test, certain conditions must be met. The first is that f of x must be positive, that is, f of x must be greater than 0. The next one, f of x must be decreasing. And then lastly, f of x must be continuous. These three conditions must be met for us to make use of the integral test. The integral test can easily be used when we have a function that can be integrated. The next one we'll be talking about is the Cauchy's n-truth test. Given the series summation a sub n as n moves from 1 to infinity, if summation a sub n is equal to the limit as n tends to infinity of the absolute value of a sub n raised to power 1 over n, or we can change that and we have it as the limit as n tends to infinity of the nth root of the absolute value of a sub n, and if this is equal to L, which is a finite number, then the series converges if L is less than 1, diverges if L is greater than 1, and is inconclusive if L is equal to 1. We also have the alternating series test. When we have a series, and in that series we have minus 1 raised to power n, or minus 1 raised to power n plus 1, or minus 1 raised to power n minus 1, then it is easy for one to quickly think of what? The alternating series test. What does it say? Given the series summation minus 1 raised to power n of b sub n, where b sub n is positive, that is, b sub n is greater than 0, b sub n is decreasing, that is, b sub n plus 1 is less than b sub n, and the limit as n tends to infinity of b sub n equals 0, then the series, according to the alternating series test, converges. If any of this is not true, then it means the series diverges. The ratio test. Given the series summation of a sub n as n moves from 1 to infinity, such that a sub n plus 1 can be determined, then the series summation a sub n as n equals 1 to infinity converges if the limit as n tends to infinity of the absolute value of a sub n plus 1 over a sub n equals to L, and L is less than 1. It will diverge if the limit as n tends to infinity of the absolute value of a sub n plus 1 over a sub n equals to L, and it will be inconclusive if the limit as n tends to infinity of the absolute value of a sub n plus 1 over a sub n equals L, and L is equal to 1. The ratio or the presence of factorial in any series suggests the use of the ratio test for its convergence. We also have the direct comparison or the comparison test. Given the series summation of a sub n as n moves from 1 to infinity, such that b sub n can be obtained where a sub n will be less than or equal to b sub n, then the convergence of b sub n implies the convergence of a sub n, and the divergence of b sub n implies the divergence of a sub n. We also have the limit comparison test. The limit comparison test is similar to the ratio test which we just talked about, but it makes use of two series. Let's look at it. Given the series summation of a sub n as n moves from 1 to infinity, such that b sub n can be determined and the limit as n tends to infinity of a sub n over b sub n equals to c. If c is equal to 0 and summation b sub n is convergent, then summation a sub n will be convergent. If c is not equal to 0, then summation a sub n will be convergent if and only if summation b sub n is convergent. Alternatively, for limit comparison test, we can say that if summation b sub n converges and the limit as n tends to infinity of a sub n over b sub n equals to c, where c is a finite number, then summation a sub n converges. Otherwise, it diverges. We also have the absolute value test, which is used to determine whether the series converges or diverges absolutely. If the summation of the absolute value of a sub n converges, then the summation of a sub n will also converge. That is, if the absolute value of the series converges, then the original series also converge. And that implies that the series is absolutely convergent. But if the absolute value of the series diverges and the original series converges, then series summation a sub n as n moves from 1 to infinity is said to be conditionally convergent. However, if the absolute value of a sub n of summation a sub n diverges and the series summation a sub n diverges, the series is divergent. In the next video, we'll be looking at how to apply each one of these tests in determining the convergence or divergence of series. If you have gained anything from today's video, give it a thumbs up, like it, and share with your friends and colleagues. Thank you. God bless you. I see you in the next video.